Welcome back to my Calculus 1 series. In today's video, we are tackling one of the most powerful tools for solving indeterminate limits, L'Hopital's rule. We will break it down step by step, look at when and how to use it, and work through some examples to solidify your understanding. Let us get started. So we use L'Hopital when we have the indeterminate form 0 out of 0 or infinity plus or minus infinity over infinity. Now, looking at this question, we have to find the limit as s approaches 0 of 3x minus sine x over x. Now, to solve this question, the first thing to remember from limits is to first evaluate at the value x is approaching. So if we put in 0, what do we get? Now, if we do that, we have 3 times 0, which is just 0, and sine of 0 is 0. So this just gives 0 out of 0. So since we have this indeterminate form, we can go ahead to use L'Hopital. L'Hopital basically means that we have to differentiate both the numerator and the denominator. So if we differentiate the numerator, if we differentiate 3x, we have 3. And if we differentiate sine x, we have cosine of x. And if we differentiate the denominator, we just get 1. So now let's try to put in 0. If we do that, we have 3 minus cosine of 0 out of 1, and 3 minus, now remember cosine of 0 is 1, so we have 1 over here, then 1, and 3 minus 1 is 2 out of 1, and this is just 2. So remember, we were able to do this because of this indeterminate form that we had. Let's look at another example. We have limit as x approaches 0, x minus sine of x out of x cubed. So we do the same thing. We put in 0, so we have sine of 0 out of 0 cubed. So we have 0 minus 0 out of 0, and this is just 0 over 0. So because of this indeterminate form, we can go ahead to use L'Hopital. So L'Hopital basically means, as we did before, we differentiate the top. So in this case, if we differentiate x, we have 1 minus, then if we differentiate sine of x, we have cosine of x. If we differentiate s cubed, we have 3s squared. So now let's put in the 0 to see if we will get an answer. So we have 1 minus, now cosine of 0, it is 1. So we have 3 times 0 squared, which will just simplify to 0. 1 minus 1 is 0 out of 0. Remember, we have another indeterminate form again, which is 0 over 0. So we can go ahead to use the L'Hopital. So we can go ahead to use L'Hopital right here. And if we do so, we are going to have limit as s approaches 0. In this case, we have, if we differentiate 1, it goes to 0. We have negative here already. If we differentiate cosine of x, we have negative sine of x. And if we differentiate the denominator, we have 6x. So this just simplifies to sine of x over 6x. So now let's put in the 0. We have sine of 0 out of 6 times 0. Sine of 0 is 0. 6 times 0 is 0. We have another indeterminate form, which is this. So now we keep on differentiating till we get a solid answer. Now, remember, negative and negative cancels out. This and this will cancel out. So we have just positive sine x. And if we differentiate sine of x, you have cosine of x here. And if we differentiate the denominator, you have positive 6. So now if we put in 0, you have cosine of 0 out of 6. And this is equal to 1 out of 6. And this is your final answer. So in L'Hopital, you will keep on differentiating both the numerator and the denominator till you get a solid answer. Let's look at the third question. we have a limit as x approaches 0 of 1 plus x minus 1 minus 1 out of 2x, and then s squared. So as before, we always put in the value. So we have 1 plus 0, the 0, minus 1 minus 1 out of 2 times 0 out of 0 squared. If we do that, we have 1 plus 0, we have the square root of 1 minus 1 and minus 0 out of 0. The square root of 1 is 1, so 1 minus 1, we have 0 over 0. We can use this in a indeterminate form. So with that, we have to differentiate the top and the down. But remember, this right here can be written as root of 1 plus x is the same as 1 plus x exponent 1 over 2, then minus 1 minus 1 over 2x out of s squared. So let's first of all differentiate this from right here. So using the power rule, 1 over 2 comes down, we have 1 plus x, then we subtract 1 from the exponent, so we have negative half here. Then we multiply by what is inside the derivative of this, which is just 1. So if we do that, we have this. Now if we differentiate 1, it goes to 0. And if we differentiate it, negative 1 over 2x, we have just minus 1 out of 2. If we differentiate the denominator, you just have 2x here. So now let's put in 0. We have 1 over 2. 1 plus 0 is the power negative half minus 1 over 2 out of 2 times 0. So we have 1 over 2, then 1 plus 0 is just 1. And 1 raised to the power any number is basically 1. So we just have 1 over 2 here minus 1 out of 2 out of 0. So this just gives 0 over 0. This is a correct indeterminate form we want, so we can keep on differentiating. So we have limit as x approaches 0. Let's differentiate this one first. So in differentiating that, using the power rule, negative 1 over 2 comes down to multiply this 1 over 2 here. So we have a negative 1 out of 4, 1 plus x. Then we subtract 1 from this, we have negative 3 out of 2. This is a constant, so if we differentiate, it goes to 0. And in the denominator, we just have 2. So now if we put in 0, we have negative 1 over 4, 1 plus x, which is 1 plus 0, raised to the power negative 3 out of 2, out of 2. So we have negative 1 over 4. Remember, 1 plus 0 is 1, and 1 to the power of any number is 1. So we have 1 over 4 multiplying 1 out of 2. So this is just negative 1 out of 8. And this will be your answer. I hope this is clear. Now let's look at, so all this indeterminate form that we had was 0 out of 0. Now let's look at a different indeterminate form. Whenever you have the indeterminate form infinity to 0, what do you do? Now let's look at an example. We have to find the limit given. We have a limit as x approaches infinity of x sine of x. Now first of all, if so, this is sine of 1 out of x. So first of all, let's put in infinity. If we do that, we have infinity sine of 1 over infinity. So this is just infinity times, now 1 over infinity is 0. So 1 over infinity is 0. So we have sine of 0. So this is just infinity, and sine of 0 that we know is 0. So since, remember, note that this is the indeterminate form that we have, and this is not the same as 0 over 0, right? So there is a way of solving this. Whenever you have this indeterminate form, what you have to do is to rewrite this expression. Now let me show you how to rewrite it. So you have a limit as x approaches infinity. In rewriting this expression, you always write this part first. So you have sine of 1 out of x, then you find the reciprocal of this. So reciprocal means 1 out of the term which is here. In this case we have x. So now if we put in infinity, right, we have sine of 1 over infinity, then 1 over infinity, and 1 over infinity, as we know, is 0, so we have sine of 0 out of 0, which is basically 0 over 0. So you see, the basic idea is whenever we have such indeterminate form like this, we are trying to make it an indeterminate form that we can use L'Hopital. So we want it to be 0 out of 0 or plus or minus infinity out of infinity. Now, since we've been able to get this indeterminate form that we want this right here. Since we've been able to do that, we can go ahead to use L'Hopital. So for L'Hopital, remember, we have to differentiate the numerator and the denominator. And if we differentiate sine of 1 over x, remember, first of all, you have to differentiate what is inside the parenthesis. If you differentiate 1 over x, you have negative 1 over x squared. That is 1 over x is the same as x minus 1, x to the power minus 1, right? So we have, if we are differentiating, negative 1 comes down, you subtract 1 from the exponent, so you have just negative 1 over x squared. That's what we have over here. And then you have, if you differentiate sine over here, you get cosine, so you have cosine of 1 out of x dividing, when if you differentiate the denominator 1 over x, you get the same thing as negative 1 over x squared. So clearly you can see that these two terms cancels out each other. So the only term that we have left is the limit as x approaches infinity of cosine of 1 out of x. And now if we do that, we just have cosine of 1 out of infinity, and 1 out of infinity that we know is 0, so we have cosine of 0, but cosine of 0 is 1. So this becomes our answer. So you see, the key idea was changing this indeterminate form to an indeterminate form that we want. Okay, let's look at a different example. We have limit as x approaches 0 from the right of x ln of x. So in this case, what we have to do, as we've always been doing, is to do substitution. So if we put in 0 right here, now remember, as I said before, 0 from the right or from the left doesn't mean anything if we are not going to have any trouble. So all that we have to do is just put in 0 here. So if we do that, we have 0, and now limit as x approaches 0 from the right of natural log of x is equal to negative infinity. So in this case, having this in mind, we are just going to have 0 times minus infinity. And if you have this, you can just invert it. So this is the same as just 0 times infinity, which is the same indeterminate form that we have over here. So in that case, as I said before, we have to rewrite the expression. So we have limit as x approaches 0 from the right. If we are rewriting, we always write the second term first. So we have ln of x here. Then we find the reciprocal of this term. So we have 1 out of x. So now let's put in 0 from the right. If we do that, this part over here goes to negative infinity as we established right here. And the denominator, 1 over 0, remember, as we did over here, 1 over 0, okay, let me write that one here. So 1 over infinity is 0, but 1 over 0 is infinity. So in that case, we have infinity here. Now, since we've gotten this indeterminate form, remember the indeterminate form that we want are this, right? So since we've been able to get an infinity over infinity, we can go ahead to use L'Hopital. So for L'Hopital, remember we differentiate numerators and denominators. If we differentiate ln of x, we're going to end up having 1 over x. Let me do division here. Now if we differentiate 1 over x, as we established, we had negative 1 over x squared. So we have negative 1 over x squared here. So this is the same as writing limit as x approaches 0 from the right. Now we have 1 over x. If we find a reciprocal, this changes to multiplication. X squared comes to the top, negative 1 comes down. So you see x will cancel this. So we just have limit as x approaches 0 from the right. So we just have negative x left. So now if we put in 0, we just have negative 0, which is 0. So this becomes our answer. So this is the second indeterminate form. So now we know how to approach 0 over 0. So 0 over 0, you just have to start differentiating. So for 0 dot infinity or infinity dot 0, you just have to rewrite the expression. You write the second term first, then you find the reciprocal of the first term. Now let's look at the third indeterminate form. We have the indeterminate form 1 to infinity, 1 to infinity, 0 over 0, and infinity over 0. Now, for this indeterminate form, we always use the same approach. For these three, we use the same approach. So we have to find the limit of the following. The first one is limit as x approaches 0 of e to the x plus x to the exponent of 1 over x. Now, let's do that. Remember, first of all, we have to put in 0. So we have e to the 0 plus 0, then 1 over 0. And e to the 0 is 1. Any number to the exponent of 0 is 1. So we have 1 plus 0. And 1 over 0, remember, is infinity, as we established right here. So we just have 1 to infinity. So you see we have this indeterminate form. Now, this indeterminate form, we don't want it. We want either 0 over 0 or infinity plus or minus infinity over infinity. Excuse me. So in that case, what do? So first of all, whenever you have this indeterminate form, what you have to do is to represent your limits by y. Okay. After doing so, introduce natural log to both sides. One thing now you have to notice, natural log and limits are interchangeable. So we can have the limits come first, natural log ex plus x to the 1 over x. And using the properties of natural log, the exponent will always come down. So you have 1 over x and ln of ex plus x. So you have this. So now, on the right hand side, let's see if we have an indeterminate form that we want. Now, if we put in 0, we're going to have 1 over 0 and ln of e raised to the power 0 plus 0. 1 over 0 is infinity. We have ln of, now e to the power of 0 is 1, so 1 plus 0 is just 1. Infinity dot, now ln of 1 is 0, so you have to note that. So remember, we've gotten the indeterminate form that we were previously working with, which is this one. And what do we do if we have this indeterminate form? We rewrite the expression, right? So in that case, we have ln of y equal to limit as x approaching 0. Remember, if we are rewriting, we always write the second term first. So we have ln ex plus x. Then we find the reciprocal of this term. So now finding that reciprocal, we are going to have 1 over, then remember 1 over x. So this is just simply limit as x approaches 0 of ln ex plus x, and 1 over x is just x. So now after getting this, let's put in 0 to see. So let me do that right here. So if we put in 0, we have ln of e to the 0 plus 0 out of 0. So this is just ln of 1 over 0, and this is 0 out of 0. So since we've been able to get this indeterminate form, then we can go ahead to use L'Hopital. So you see the basic idea, we change the indeterminate form to get what we want. So now the next thing is to differentiate the numerator and denominator. So to differentiate this, remember, whenever you have natural log and you're differentiating, you always differentiate what is inside the parentheses first. So if we differentiate e to the x, you have the same thing. And if we differentiate this x, you have 1. Then you divide by what is inside the parentheses. So you have ex plus x. Then you divide everything. Now let's differentiate the denominator. If we differentiate the denominator, you have 1. So you can go ahead not to even bring this because we are dividing by 1. So now if we put in 0, you are going to have e to the 0 plus 1, and e to the 0 plus 0. So e to the 0 in this case is 1 plus 1, and 1 plus 0. So this is just 2. Remember, we have ln of y equal to this whole thing, right hand side. So we have the left hand side to be ln of y, and the right hand side will simplify it to be 2. And now to find your y, we have to find the inverse of natural log, and which is exponential. So we have this e squared. So e and natural log always cancels out to each other. So you have y equal to e squared, and this is going to be your limit. So this right here is your answer to the problem. So always represent it by y, then introduce natural log to both sides. Okay. Let's look at the last question. So for the last question, first of all, let's put in infinity. Remember, limit as s approaches infinity of ln of x is equal to infinity. So in this case, if we put in infinity right here, we're going to have infinity and 1 over infinity. And 1 over infinity is just 0. So we have this indeterminate form. We can't go straight ahead to use L'Hopital, right? So remember, whenever you have this indeterminate form, we represent everything by y. So we represent the whole expression by y. Then after doing that, add natural log to both sides. Then we can interchange limit and natural log. So we have this one first. And in this case, what we have to do is, remember, for natural log, the exponent always comes down. So we have ln of y, limit as x approaches infinity, 1 over x, ln of x. So what do we do in this case? Let's try to evaluate the right hand side. If we put in infinity, we have 1 over infinity, ln infinity. 1 over infinity, as we know, is just 0. So we have 0 right here. And now we have ln infinity is also infinity right here. And what is ln of infinity? That one goes to 0. Ln of infinity is still infinity, right? So we have over here, we have 0 dot infinity. And remember, if we have this indeterminate form, we will write the expression. So we have ln of y. And in rewriting the expression, remember we write the second term first. So we have ln of x. Then we find the reciprocal of this. Reciprocal of 1 over x is just x. So let us continue here. So if we do that, we have ln of y. Now let's put in infinity. We have ln of infinity. Then the denominator is infinity. We have ln. Remember, ln of infinity is infinity. Ln of infinity is infinity. So you see, we have an indeterminate form that we want now. So now we can go ahead to use L'Hopital. So for L'Hopital, we differentiate the top and the down. So in that case, we have limit as x approaches infinity. And if we differentiate the numerator, which is this, we have, so note, this is very tricky, right? In differentiating this, we always differentiate what is inside the parentheses. So if we differentiate ln x, we have 1 over x, and you have to divide by what is inside the parentheses, which is just ln of x. Okay. And if we differentiate the denominator, which is x, it goes to 1. So basically, it does nothing to our question, so we can choose not to even bring it. Okay. So now let's rewrite this. So this is the same as writing ln of y, limit as x approaches infinity, 1 over x over ln of x, the same as 1 over x ln of x. Okay. So now, let's put in infinity. On the right hand side, if we put in infinity, we have 1 infinity ln of infinity, and this is just 1 out of infinity times ln of infinity is infinity, right? So it's infinity times infinity is still infinity. So 1 over infinity, remember, is 0. So we have our ln of y to be equal to 0. And to find y, we have to find the inverse of natural log. So we have this. So now we have just y, and e to the power of 0 is 1. So we have our answer to the question as 1. Okay, so this is the end, but before I end the video, let me do some recap. So now we've gotten to know that if we have this in a indeterminate form, you just go straight ahead to differentiate the top and the down. If we have this in a indeterminate form or this indeterminate form, we will write the expression. Remember that. And if we have the indeterminate form 1 to the infinity, infinity to the 0, or 0 to the 0, which is what we have over here. In that case, we represent everything. We represent the expression by y and add natural log to both sides. I hope this helps. So that wraps up our exploration of L'Hopital's rule. I hope this video helped you gain a clear understanding of how to approach indeterminate limits using this method. If you found this helpful, don't forget to like the video, share it with friends, and subscribe to the channel for more calculus content. Thanks for watching, and I'll see you in the next video.